So yeah, we are just going to like prove some basic formulas. I think about 4 or 5 of them. That's what we are about to do here. So I thought I might be able to do video on test of significance before, but I don't think I can. So before the proving, I'll just like quickly brief on what it's all about. The test of significance. So I will encourage that you go to Kusoyanis. So far, I think Kusoyanis is still the best material that explains it better. Is it Kusoyanis? Yeah, Dr. Just material to kind of do a great justice to that. You can mix it up with Kusoyanis. So let me go to that test of significance first. Now, hypothesis testing. That's majorly it. Remember that I said that the 8 models, what we are just doing this semester is basically 2 of them: the estimation part, which is the OLS part, which I briefly discussed, and the hypothesis testing. After we have estimated our beta 1 and beta 0, our 2 betas, we now want to test our estimation. Does it make sense? Is it rubbish? Is it following the rules that it's supposed to follow? You know that we are talking about reality here, so we have to just keep testing till we are very sure that okay, this is actually disputing reality. So that's what hypothesis testing is trying to do. We are trying to test if all what we are doing is actually good. Now we want to test how good our estimated betas are. How good are they, like representing what we want them to represent, the population. So that's why we call them that's why we classify them as the goodness of our parameter estimate. That's what hypothesis testing want to just do. We want to check the goodness of our parameter estimates. Our parameter estimates are our betas, beta 0 and beta 1. Beta 0 and beta 1. So we want to see how good they are. So in order to see how good they are, we basically need so in order to test it, we basically have 3 stages. We like call them stages. Yeah, 3 stages. We call them the criteria for judging the goodness of the parameter estimate. The criteria for judging the goodness of the parameter estimate. So the 3 are the theoretical, which is also called a priori criteria, the statistical, and the econometric criteria. Now let me just talk about the theoretical. Now after you have gotten your betas, remember that your estimated betas, beta 0 and beta 1, is trying to represent your population beta, which we don't know. We don't even have any idea how it looks like. We just know that because we are talking about demand, there should be a negative relationship, but we don't know what should be our constant, our beta 0, what should be our beta 1. But we have not estimated it with our OLS. We have estimated it that the demand function, or let's just use our normal function, but it's still representing demand, y is equals to beta 1 is 10, beta 2 is -4, then x. Let's assume this is what our function is giving us. This is what our function is giving us. I can add mu. Maybe just add mu in case we need it. So let's assume this is what our function is giving us. I'm focusing on these 2, for example. So our function is giving us this. Now after getting this, we now want to test, is this our estimate? The both of them, are they really following what they should be following? Are they really representing our parameter? So we want to actually test how good they are in representing our parameter, which is the real beta 1 and beta 0. So to test that, we start from the theoretical part. That's the a priori. What we just do here is that we look at it. Is it even following the normal rule of demand? Remember that this example I said it is for demand. Is it following the normal rule of demand? If it's not demand, if it's any other theory, is it following the normal rule of any other theory? Suppose you have estimated your beta 1 and it has given you +4. Remember that demand have the inverse relationship. It simply means everything you have done, all your estimation is wrong. Why? Because it's not even following the basic rule of demand, which is the higher the price, the lower the quantity demanded. So which have a it shows a negative relationship. But this is not showing a negative relationship if it's +4. It simply means it has failed the test of a priori expectation or a priori criteria. So it simply means you are going to reject, you are not going to accept this estimate as a good estimate. It's not really representing it. So it must always follow this theoretical. That's why I believe that this is the most important criteria among the 3 criteria, because even if it follows order, if all these are right, but this is wrong, you still will reject that this is representing your population parameter. So you are going to reject that it's representing your population parameter because it must follow the basic rule of demand or of whatever parameters you are using, whatever example you are using. So that's the first one, which states the theoretical or the a priori criteria. That's the first part. Now, this part majorly is talking about the sign and size. That's basically what this part is talking about. Because most of the time, our economic theory, that's just what it's always talking about. When we talk about law of demand, it's not actually telling us anything than the sign and size. Then it's going to tell us that there is an inverse relationship, that's the sign. So that's majorly some may not even tell you the size, but some go to the extent of telling you the size. So this a priori is just basically the sign and size. So once you see that the sign is not the sign that's supposed to be there, this really means your estimate is wrong. So once your sign is supposed to be positive, for example demand, now like the relationship between income and demand, it's supposed to be positive. The higher the income, the higher the demand. And you are seeing that it's always giving negative. Or your supply that is supposed to be positive, you are seeing that you are having a negative sign. It simply means you have not estimated rightly. There are many reasons that can cause it. Maybe you got the wrong data, you make mistakes, so many reasons. But this is just very important for your model to be able to meet up this criteria. You have to follow this criteria. So this is the first stage. This is the first criteria that you must ensure that your model is following. You must ensure that your model is following. So if your estimate of the parameters go against this particular expectation, it should be rejected. Unless there's a good reason. There's a good reason for that particular principle not to hold. But let's leave that good reason. Once it's not following it, just reject it. It is not wrong. So let's go to the statistical part. So if your model passed this test, passed this criteria, good. So we now look at it statistically. Now, okay, since this is good, let's look at it statistically. So we are doing statistical tests now. So this particular test, they are of 2 types. The first one is what we call coefficient of determination R squared. Coefficient of determination R squared is simply the square of your correlation coefficient. There are 2 different things. Correlation coefficient is R. Coefficient of determination is R squared. So R squared is one of the type of statistical tests, and the second one is standard error. So the 2 of them are very, very important. This statistical is just basically meant for you to test the statistical reliability of your model. Statistically, can your model be trusted? That's just what you are trying to do. And we use the R square, that's coefficient of determination, and the standard error to check this. Now the R square, what do we use the R square to do? We use to test the goodness of fit. How good or fit is your regression function line? That particular line, how good or fit is it? So how well is their sample regression line representing the population regression line? So that's what we are trying to test with your R square. While the standard error, we want to look at how good is your estimate. What is the statistical significance of your estimate? That's what we are trying to do with the standard error. We want to judge if your estimate is statistically significant. The first one, you are looking at the goodness of your fit, the goodness of your line. While the second one, you are looking at the statistical significance, that R square and standard error. So R square have its formulas. When we are doing the proving of the formula, you are going to see some of the formulas of R square and how to prove them. Standard error to have its own formula. We are going to use more of that whenever we are doing like the main issue H1, where we are like testing our hypothesis and so on and so forth. Unfortunately, we might not be able to do that. I wish I could do that, but I'm not sure that will be possible again because of time. So econometric is the last test you are going to criteria you need to follow. Once you have passed through the theoretical, statistical, the last part is the econometric test or criteria. So yeah, we are just trying to use a set of some econometric theory. We want to see if our assumptions of econometric, we want to see if it's actually following through. We want to see if the assumptions of econometrics, if they are actually true in our model, if our assumptions are actually true in our model. So we want to see how reliable our model is. After they are free from standard error, they are free from all the errors we think they might have in the past by using the theoretical and the statistical. We want to see, are they violating the rules, the theory, the assumptions of econometric, which are basically the assumption of autocorrelation, the assumption of multicollinearity, the assumption of heteroscedasticity, and model specification. So we want to see if they are not breaking any of these assumptions. So that's basically what we are doing in the hypothesis testing. So let's go back to proving our formula. So the first formula we are trying to prove is our beta 1 and beta 0 formula, the formula that we used to get our beta 1 and beta 0. Mind you, these two formulas, they have like various formulas, like 2-3 formulas each. So we are going to like, I think we are going to like prove so many of them, if not all of them. But let's start with the first formula, the one that Mr. Bushi used for us, and the one that is like very common. The one that is like very common. So that's the one we are starting with. Now we start majorly from this our two function. We have the population function. Remember that the population function is like this. We have our yt is equals to bu plus b1 xt plus mu t. This material, the first one I used for the summarized material PDF that I just used for the video. I'm going to share it on the group chat, and this formula combination, so I'm going to share it to the group chat, so in case you need it. So let's continue. So this is our population regression function. Remember, our population regression function does not have at. It does not wear at. So no at for population regression function, and that's our real function. We're simply saying that our dependent variable is equals to this constant, which is the intercept, plus the slope times our explanatory variable, then plus the error term. That's our population regression function. That one is known. You might be given this, might not be given, so you have to know how to write the population regression function, which I believe many of us should know how to write it. Remember, this t is simply showing time series, which simply means you are looking at a particular subject over different time. So it's showing the time series, but that's never our focus here. Just put your t. So our sample regression function is the one that now carry at. Y at is equals to beta at plus beta 0 at plus beta 1 at times xt. The xt does not have at, I just want you to take note of. So it's only all these ones that have at. So with this, remember that we don't have mu here. But we can also have an estimated error term. The estimated mu is just like mirroring the real mu here. Everything here is just mirroring what is here. This y at is mirroring this. This is mirroring this. So we want to try as much as possible to get exactly the same thing, or very close to what we have in our population. So it simply means this our mu will be almost exactly the same thing as this our mu. So from what we have here, this guy and this guy, by the time you minus the two, you see that you have something like this. By the time you minus this first one, you minus the second one from this first one, you are going to see that this one will cancel this one will cancel this one. So you are just going to have that u is equals to this minus this. By the time you minus, so that's how we get this these two, they are gone. So this u will just be equals to this minus this yt minus yt at. That's how we got this. So moving further, we now have it as this. Now the definition of OLS simply means sum of squared. That's just the simple definition of OLS. That means you find the square, you now find the sum. So that's just what we are going to do here. So we are going to square. Don't mind me, I started with summation here, but it doesn't change our answer in this particular instance though. But you can always start with square. So we squared our mu here. We squared this side too. So you square both sides before we now add sum of everything. So that's how we get it, sum of square. That's the definition of our OLS, sum of square. So that's how we get to this particular place. Now from above, we already know that our estimated y, that's our sample regression function, is equals to this. So just remove this guy here and put this. Now one of the most important thing in this is that is your sign and bracket. Don't joke with signs and brackets. You don't need to mind if you have to write 20 brackets on the same line. So far it's not going to make you to make mistake. So the bracket will help your signs too. So make sure you don't make mistake with your signs. Like this beta 0 as plus beta 1 as. By the time you put it inside here, it becomes minus beta 0 as minus beta 1 as. If it may be difficult for you to do it directly, first put it inside brackets before you now open the bracket. The signs are very important. The signs and the brackets are very, very important. So when we put this inside this, it becomes minus. So we have yt minus beta 0 at minus beta 1 at, then xt. Everything is still squared. So this is now where we are now, our equation. These are where our equation is. Now we now to apply the minimization rule. Now part of the OLS definition still have that we minimize it. So we minimize this particular function. I like that. This particular function. How do we minimize it? We are simply differentiating and equating it to 0. That's how we minimize it. So we differentiate with respect to each of the estimated ones we want to use, beta 0 and beta 1. So we differentiate with respect to beta 0, we differentiate partially with respect to beta 1. So we have two different equations. So when you differentiate with respect to beta 0, now this is still the same way you are differentiating. It does not change. The issue is just that we don't have exact numbers as we do have. Like we don't have exact number, we have like complex number, not like complex number root to minus 1, but complex number like not even number, letters, alphabets that we are using to represent it. So it's still the same thing you are doing. So when you are differentiating with respect to beta 0, for example, what you just need to do is to use what is it called, chain rule or generalized power function. They are still like the same thing. So and then you use your chain rule, you can represent this one with u. By the time you represent it with u and use your chain rule, you are going to get u squared, because this one half squared. You are going to get half u squared. So by the time you find this over the u over the beta, you are going to have 2u. And by the time you now differentiate this one itself, you are going to have minus 1. So that's how we now get to this final one. I believe you should be able to get differentiation. That's why I'm not like emphasizing on it. If not, you can easily visit Schwanz or any other material that I think can quickly remind you about differentiation. So that's how we have our final answer. By the time you differentiate, you have it here. So these are final answers differentiating with respect to beta 0. These are final answers. And remember, we equate it to 0. So we now divide both sides by this minus 2, so that this minus 2 will be out. So we now have only this part. So this is the part we have here now. So after having this part, we expand it. How do we expand it? remember that the summation is for all of them, so you multiply each one of them by the summation. That means you use summation times this, summation times this, summation times this. By the time you multiply summation times this, it becomes summation yt. Multiply summation times this, it becomes summation b0. But b0 is basically a number, so you just put n. N simply means the total number we have, the total size, like the sample size. So you just use n. Whenever we have this beta, we just use n. Then summation times this, it only affects this xt. But now that's summation beta 1 times summation xt. Everything is equal to 0. So by the time you now bring this particular guy, these guys, you bring them to this side, they all change to plus, and this one is standing on its own. So we have summation yt is equals to this. So that's what we have now. Because this one is minus, when they come here it becomes plus. This one is minus, when it comes here it becomes plus. So this is what we now have for when we differentiate with respect to beta 0. So we do the same thing with respect to beta 1. So this is like one of our equations. So we are now doing the same thing with respect to beta 1, differentiating with respect to beta 1 using chain rule 2, and you equate it to 0. So after differentiating with respect to beta 1, we get this. So we got this too. So we have this after differentiating with respect to beta 1. We actually have this, but we divide by minus 2 to remove the minus 2 out. So we now have this left. This is now what we now have left. So after having this left, the same thing, you expand, you multiply with xt, you still multiply with summation. So you simply give us the first one, give us this times this times this, summation xt yt. That's how we get this. The second one, you still do the same thing. This one xt now times beta, that's beta 0 minus beta 0 times summation xt, this summation xt that you multiply with beta, minus this summation st times this one. So we have minus beta 1 summation xt squared, because we now have 2xt. So that's how we get this. Then everything is equal to 0. Then you rearrange to, you bring all the guys here, you bring them to this side. So we now have this as our final answer. As in, not final, but let's say semi-final. Yeah, semi-final for World Cup. Yeah, this is like our semi-final answer. So we continue. We have gotten two equations now. After differentiating with respect to b0, we have one equation. We differentiate with respect to b1, we have another equation. So I think I go to the two of them. Yeah, these are the two equations we now have now. The two equations. This one equation, this another equation. Now we look at this. It follows simultaneous equation with two unknowns. This is an unknown, beta 0, beta 0. This is another unknown, beta 1, beta 1. All these ones are just representing coefficients. No matter econometrics, it's still math we are doing, just that the math is now using number, it's just using letters throughout alphabet. Don't tire me too. So this guy and this guy too are actually representing number. That's your solution. So with this, you can just use your simultaneous equation with substitution, elimination, and but substitution elimination will definitely give you problem here, because these are not numbers. These are alphabets, symbols, and so on. So the best thing you can do is to use your matrix. Convert them to matrix. How do you convert to matrix? This first two, you may by 9 minutes. This last two, this is it. Then your unknown, put it in another bracket. Then your solution, the answers, put them here. Then you now apply grammar school. Grammar school in matrix, which simply means that you are going to find the determinant of this. After you get your determinant, write it, let's call the determinant A. Then you switch these two guys and put the solution. The solution will come here. So you now find the determinant of your new matrix. Let's call that one A1. So you are going to divide A1 by the normal A. That means your normal A is your normal determinant before you switch. But your A1 is now you switching your first column with the solution here and find the determinant. That's the A1. That will be B0, the answer for B0. The answer for B1 is still over A2. That same determinant that you find before you switch, that's A. Then you now switch this one with the second rule now. The first rule will still be the same thing, n over this. You switch this one with the second rule now. You are not switching with the first rule. You switch with the second rule now. You get your, let's call that one A2. So by the time you divide your answer, that will be your A1. So it is after finding the determinants. So I wish I could use what's it called, pen. I try to use pen to like write it out. That would be easier for me to be able to solve. I cannot be using mouse typing, writing all of this. That's why I just have to write them out and explaining with it. I have worked to like do the grammar school out itself. But I believe if you go to matrix in mathematics, you should be able to get the grammar school. So by the time you do that, you have your A1. This is your A1 here, the answers for your A1 after you find the determinant. Then over the answers for your A itself. So that's how we get our beta 1. So we have just put that formula just like that. That's just the formula, beta 1. The same thing goes for beta 0 too. You do the same thing. That's why you prove for beta 0. So beta 1 and beta 0 have been proved. So that's the formula for beta 1 and beta 0. Proving it. Don't forget the steps. You start with using the definition of OLS. Or you start with your population regression function, your sample regression function, you compare the two, you get a particular equation. Then you apply your definition of OLS, which simply means minimizing the sum of squares. So we start with sum of square. So you square it, you sum it, then you minimize that particular square and sum. So minimizing it simply means that you are differentiating and equating to 0. So after differentiating and equating to 0, you get two equations. That means you differentiate with respect to beta 0, differentiate with respect to beta 1. Then you have two equations. Then you now use grammar, so then you get your answer. So I'm now writing it out. So this for beta 1, this for beta 0. So you have proved those two formulas. But beta 1 can also be this. This is another formula for beta 1, or this. So we are going to prove this to now. Beta 0 can be this. I'm not sure I'm going to prove this one. I don't know how to prove it. I'm not sure. But you can still use scope. By the time you see it in the exam, you may use scope. But I don't think I have the time to like check this out yet. But let's check the one below. Okay. Beta 1 can still be this too. Beta 0, can still be this. Beta 0 can still be this. I think this one is easy to prove though. This first one, this one here, is easy to prove. You just make beta 0 your subject of formula from your sample regression function. That's it. Beta 0 you make it your formula for your sample regression function. But we are going to prove this now. We are going to prove this. We are going to prove this. This one and this one, they are the same thing. So once you prove this, you have automatically proved this in a way. So we are just going to prove this, this, and this now. That's what we are going to do now. So you can use any of the formulas depending on the type of data, the type of information you have available. You can use any of the formula. This for beta 1 stop here, and downwards is for beta 0. You can use any of the formula in your questions, in your solution. But how to prove it is what we are looking at here. How to prove it. So we have proved this first two. Let's not go to the ones that I said we are proving now. So to prove this first one, the one for beta 1, let me highlight it. And I said it's the same thing as this, so we put the both of them together. And while proving it, we will see that we will prove this one too. Just take note. This one is beta 0. It means mean of y minus beta 1 at times mean of x. That's another formula we can use for beta 0 when we know beta 1. So we are going to prove the three together at once. Yeah. So to now do that, I've written out in steps. I think these steps easily help people to like get, especially when we have something that's complex to solve. Steps really help. You don't need to count the steps. This is not official step. It's not that you must leave at step 1 I did this. No, it's just for personal use. You can use it personally. So don't need to list the step. But majorly, whenever you want to solve it the first time, second time, third time, the steps will just guide you. Do this first, do this first. But after the third time you have solved it, I don't think you will need steps again. Everything will just be in your head and you'll be able to like solve it yourself. Yeah, the magic of mathematics too. So these steps, the first step, second step, third step, yeah, just get it through, you get the steps. But I'm just going to start with the solving directly, omitting the steps. I just put the steps in case you need it for your first, second, or third solving. So this is actually what we want to prove. This is it here. Same type of what I put up here. This is actually what we want to prove. So how do we go about that? How do we go about that? So it's down here. So it's down here. You actually have to start. Sorry, I skipped step here because of time. You actually have to start from here to this same population and sample regression function. You actually have to start from here, and you are going to keep doing the same thing. You keep doing the same thing that you did here from the beginning. You keep doing it. That means you find the sum of squared. After finding the sum of squared, you minimize and equal to 0. You get your equation 1 and equation 2. That means you minimize, you differentiate with respect to b0. You get your equation 1. Where's equation 1? No, this is not equation 1. Equation 1 is down. Okay, this is equation 1. But you don't make anyone the sorry. You may not need to make anyone the sorry of formula here. Let me note equation 1. This is equation 1. Then differentiate with respect to b1 to get your equation 2. This equation 2. Yeah. So differentiate with respect to b1 to get equation 2. This equation 2. So after you get to that stage, you will not follow this method again. You now continue with this particular piece I'm starting with now. So that's why I am saying that starting from the minimization. So after you have minimized and you have gotten your equation 1, see your equation 1, you differentiate with respect to beta 0, you get equation 1. So I've noted it here. You differentiate with respect to beta 2. For your equation 2, you differentiate with respect to beta 2, you get your equation 2. So those are the two equations. Now you now start to continue following the steps. The step I listed above, you see everything I'm going to do here, I've listed in that step. Trust me, just follow that step. Try it like 4-5 times. Following that step. By the 5th time you're doing it, you will not need the steps again. You'll be able to like solve it without the step. So the next step is to divide equation 1 by n. So this equation 1, divide everything by n. It simply means summation times y1 divided by n is it here, minus beta 0 times summation. Remember the summation will multiply the 2. Summation times beta 0 will simply make the summation become n. That's n times beta 0. Everything divided by n. Remember we are dividing 2 by n. Then summation times this. You simply give this beta n. Then xi. You also have summation. Then everything divided by n. Then you divide 0 to by n. So this guy, the first one, summation yi divided by n. Yeah, another thing I also like doing whenever I want to prove the second formula like that, I don't like using t, I like using I. But I don't think that should matter though. I like using I. In fact, sometimes I may not even use I and t because all those things actually make the equation look longer. But just to be on the safer side, I think I can use any of the two. You can use I preferably. So summation yi divided by n simply means mean. Why do we say that? Because summation yi is just trying to tell us that the sum of all the observations you are given, then divided by the total number of observations. That's the definition of mean, for God's sake. So if you have observation 2, 3, and 5, and they ask you to find the mean, you are just going to sum 2 plus 3 plus 5 divided by the total number, that's 3. That's exactly what this guy is saying. So that's why we simply change this guy to mean of y. Minus n will cancel n for this one, so beta 0 will stand alone. Minus n will cancel n here, but this n will still affect this summation too. So n will cancel n here, this one become beta 1 times this one now is also mean again, but it's now mean of x, this place. because it says summation of all the observations divided by the total number of observations, and 0 minus n, sure, this one remains 0. Now the next thing is now to make b0 here the subject of formula. So this b0, when we make it the subject of formula, we get to this place. So I wrote first proof here. Remember I said that we are also going to prove that b0 is equal to mean minus beta times mean of x. So we have proved that one. In case you are told to prove this one, so this is where you just stop, just off your engine here. So don't off your engine because you need it for the next question. So that's just on the vital note. So let's just continue. So let's now assume we are not asked to do this. We want to continue. So since we want to continue, the next step is now, this is your equation 3. So don't forget that. You now go back to your equation 1 and multiply it by x. You multiply equation 1 by x. So your equation 1, where is it? Come up here. This is your equation 1. This guy here. This is your equation 1. So you multiply it by x, not just x, mean of x. So that's how we get mean of x times this. So that is in your equation 4. Now your equation 2, you have not been using your equation 2 so far. This is your equation 2, that differentiation with respect to b0. So you now see your equation 2 minus this new equation 4 you have got in here. Don't worry, everything is in, I've written it out in that steps above, so you can just check it. And I said I'm going to share this material with you, so you don't need to write it out again. It's already in your steps, in the PDF I'm going to share. So they're just going to like minus 2 and 4, 2 minus 4. So that's how we get this, our equation 2 minus equation 4. We have this here. Now this one is actually very simple, as in this place is actually very simple, as in it's just like your 2 minus 1 and 4 minus 2, but we don't have 2, we don't have 1, we have alphabet and symbols here. So your most important thing is your bracket and your signs. The reason why the bracket is important is because of the signs. The bracket will determine the signs in many ways. So, and also it is also going to determine your multiplication and co. Wow, this video is becoming long. I wish I would be able to break it. So I think after this particular proving, I'll just break it and like do another video for the remaining provings. So as I was saying, your bracket and your signs are very important. So how do we minus these two? If you look at this, this is like the same thing as this. This guy, two guys here are the same thing. So like I'll just bring out my summation out first. So it remains these guys and these guys, they are the same thing. So it's simply using, for example, when you have 2x, now let me use 3x minus, or let me use 5x, sorry, 5x minus 3x. Now how do we do this? We simply get 2x. How do we get our 2x? We simply see 5 minus 3, that's 2. Then we pick one of the x. The same thing you are going to do. You are just going to say this x1 minus x bar. Then you pick this particular guy, since they are the same thing, and put it in front. But your x1 minus x bar, put it in bracket. This is it here. Then this one that you just pick one of it, since they are the same thing, this is it here. Then your summation, which is in both of them, factorize it out. This is it here. So that's how we get this particular one here. So the next step is now to substitute beta 0 with equation 3. The equation 3 that we get just now, I will say is another proving on its own. Let me just show you. On there. This equation 3, you are now going to substitute it to what you have now. So it simply means our equation will now be, this guy will still remain the same, this is it here, y1 still y1 minus b0, then remove that b0, beta 0, the minus is still there, then put your beta 0. It's very important you put it inside this bracket so that it will be able to affect the signs. If not, if you don't go and put the bracket and you can't make mistake in the signs, everything will just be scattered. I put it will be scattered here in the example. So I put in the bracket, then minus this last one to still remain the same. So we now have summation this, while by the time you open the bracket, minus times this, y minus y bar, minus times minus, that's plus beta 1 x bar. So that's how we get this one. So we continue. So where are we? Okay, we are here. So after doing that, we now factorize this one inside this bracket. This guy is not giving us problem. We cannot do anything with it yet. So we just leave it that way. But these two guys, can put them together so that they look like this. So this is what I did here. But I put them inside a bigger bracket. Remember that it has bracket normally. So I put them inside a bigger bracket. Minus this beta, this two beta is common. So I bring them out. Now this can be plus, this can be minus, but I advise you use minus because of the steps you want to do now. So you just bring out minus, that minus beta 1 is common in the 2. By the time you bring out minus beta 1, this x bar will not more be plus x bar, it will become minus x bar. This minus x1, you have removed beta, you have brought beta out, will no more be minus x1, will now become plus x1 because of this minus we brought out with it. So that's how we get this. So you now rearrange. We have minus x bar plus x1i. We want to make it xi minus x bar now. It's still the same thing. So we just, the issue is just that the major thing is I want it to look like this. So, but if we do not use minus here, it's not going to look like this. It's going to look like x bar minus x1. Well, that is different from x1, xi minus x bar. So that's what we want. So by the time you bring out minus beta 1, this will remain minus x bar plus xi from here. You'll be able to get this. So we now continue. We now have summation this. Then inside the big bracket we have this minus x bar. Then we arrange this si comes like this. It still remains xi minus x bar. So that's how we now have this. They will now use this guy to multiply this. You use this guy to multiply this. That's why your big bracket is important. Suppose you have mistakenly omitted your big bracket, you will not know that you have to multiply this with the two of them. You might just multiply this with this alone, but that will be wrong. So you need to multiply this with this, multiply this with this. So now I have summation inside our bracket, outside. Then we have this times this, it give us this. Then we have this again times this, then give us minus beta 1. Then we have x1 minus x bar squared, because they are the same thing now. So with this, our equals to 0 that we have removed since all these years, just equate it to 0. So then you make beta 1 the subject of formula. That means this beta 1 makes the subject of formula. So by the time you are making beta 1 the subject of formula, let me scroll down. By the time you are making beta 1 the subject of formula, we are going to have beta 1 this is equals to this. Then divide both sides by this here. Then we have beta 1 is equals to this, which we have just proved. Then which is equals to this. So that is how we just prove it. That's how we just prove either this one or this one, because the two of them are the same thing. Once you prove one, the other have been proved. So I'll just end this video here. Then I think the next formula is R squared family. R squared family. R squared is the coefficient of determination. Yeah, R squared family. So we are going to look at the R squared family very soon, but let me just create a new video for that. Thank you.